I'm sorry. Now Elies is going to talk to us about the model of linear logic using polynomials and homotopy type theory.
Thank
Go
you.
ahead, please.
Hello, everyone. Very thankful for being here. My name is Elies Harington. I'm a senior PhD student working with Samuel Mimram. And so, first, what's this all about? This all dates back to 1988, where Jean-Yves Girard published this paper about normal functors as a model for the n-type lambda calculus. And this model of normal functors is based on a category of normal functors, which is a Cartesian closed category, which is the basis for models of the n-type lambda calculus. But since we're talking about functors here, we actually have two category of like categories, normal functors and natural transformation. And these two categories was not Cartesian closed, and it was already observed at the time. So normal functors are nowadays known more as a special case of the notion of polynomial functor. And 3 years ago here at MFPS, my advisor Samuel Mimram talked about a Cartesian bicategory of polynomial functors in homotopy type theory, which is a generalization of normal functors in homotopy type theory to get actual bi-Cartesian closure. Cartesian closure in the sense of bicategories. And what I'm going to talk about today is a bit about that and how actually this fits into the big picture of a model of linear logic. So I'm not going to tell all the details of linear logic for those who don't know, but the main idea is that instead of having ordinary implication as in classical logic, we separate implication as this kind of linear implication represented by this lollipop here, and this exclamation mark called a bang or exponential modality, which basically allows you to duplicate your hypothesis. So a linear implication is a proof of implication that only uses every hypothesis once. And when you have a bang in front of an hypothesis, you can actually use it as many times as you want. And so this is a way to decompose classical implication. So what are polynomials in sets? A polynomial is an expression of this form. So here I haven't written any coefficients, but you can always represent at least natural number coefficients just by repeating sums of the same monomial. And here everything is a set. So here I'm summing, of course, over a set B, and I'm taking a variable x to the power of a family of sets AB. And so since we have sets everywhere instead of numbers, this is a kind of categorification of ordinary polynomials. And they are more often presented not in this indexed way, but in this fibered way. So whenever you have a family of sets over a fixed set B, you can take the union, the disjoint union of this family, call it big E, and the projection back to B. And those two data are equivalent. So the data of a polynomial can just be encoded as a map of sets. Just remember that the set B is the set of monomials, and the fiber over a small b is the exponent of this monomial. And whenever we have a set like this, the expression we had before can actually be seen as a functor from the category of sets to itself. Because here, taking sums and taking powers, finite powers, or even arbitrary powers and products, this is all functorial. And so this is just functors obtained as sums and powers. Just a little example here. Let's take a set B with 3 elements. So we're going to get 3 monomials. Here, one monomial with our exponent 2, because it has 2 elements mapped to it. This gives us x squared. One element with just 1 element in its fiber, that gives us x. And of course, you recover the constants by having stuff with empty fibers, because x to the 0 is just a singleton. So this represents the functor x squared plus x plus 1. And it's possible to generalize polynomials to have input and output colors. And what this means is, instead of having just one polynomial in one variable, you get a family of output polynomials with several input variables. So here, for instance, I have 2 output colors and 2 input colors. So here I have suggestively named them x and y because they represent 2 different variables, x and y. And here I have one monomial with the color that will be on the left here. This monomial takes a product of 2 things. One of them is an x and the other is a y. So we get xy. And here I have 2 monomials. So I'm taking a sum. of one monomial, which will just be an x, and one monomial which will just be a y, so x plus y. And as you can imagine, those things actually compose. So in general, if we have any set I and j, you can define polynomials between I and j as being diagrams of this form. They always induce polynomial functors between sets to the I and set to the j. And when you take a composition of polynomial functors, it is still polynomial. And it's actually possible to write at the level of diagrams how to compose those kind of diagrams. But when you do it that way, you no longer get a category, because when you compose functors, composition of functors is strictly associative, but the composition of diagrams, even though it represents the same composition of functors, it's only associative and unital up to isomorphism. And so you actually get a bi-category, or if we only care about two isomorphisms, a 2-1 category of polynomials and sets. Now, since I'm going to talk about linear logic, I'm going to need to have a notion of linear morphism. And among all polynomials, the linear polynomials are those whose exponents are just 1. So here in our case, since we're talking about sets, it's just singletons. And in the fibers point of view, if all the fibers of this map are singletons, this means that this map is an isomorphism. So up to isomorphism of polynomials, a linear polynomial is the same thing as just a span, because we can always consider this isomorphism to be the identity. And when you see linear polynomials as spans, their composition as polynomials is actually the ordinary composition of spans by Toolbox. So now we want to have a model of linear logic. So we have on one side the polynomials, the classical implication, and on the other side, we want to relate this to spans. So here, this should be a kind of adjunction. So for a kind of functor, an underfunctor on the category of spans, or something going from spans to polynomials, something like that. There are a lot of possible different presentations for this, and I will tell you later exactly what kind of model of linear logic I'm considering. But so the question is, what should we put here to hope something an equivalence of this form? So if we just take I and j to be singletons and consider for a moment polynomial functors between set and set. They are entirely determined, as I said before, by a base set of monomials and a family of sets giving the exponents. And so this is just a set B together with a map to the set of sets. And there's always a trivial map to a singleton. So this seems like a good thing. We managed to reduce the data of this polynomial to the data of a span. And so we would like something along the lines of bang of 1 being sets, the set of all sets, which is something that sadly does not exist. And so in order to make sense of this, we're going to have to restrict our polynomials. For instance, we can restrict the exponents. And if we restrict exponents to be finite sets, we can here replace set with finite sets or natural numbers maybe, and get something that actually lives inside the category of sets. So that's exactly what we're going to do. We said that the polynomial is finitary or finite if all the exponents in its definition are finite sets. And we use this notation for the type of finite polynomials between I and j. Just to make sure that we're clear here, being finitary means that the exponents are finite. So this polynomial here is of course finitary. This one is also finitary because even though you have an infinite coefficient, this just represents an infinite sum indexed by the natural numbers. Here we have an infinite family of variables mapped to an infinite family of polynomials with unbounded coefficients, but this is still finitary because all the exponents themselves are finitary. And so an actual infinitary polynomial would be one where you have like an infinite set in the exponents, which is not something that people would usually call polynomials in the regular sense, but it's something that exists when you do category 5 polynomials. And just as a semantic check, linear polynomials will always be finitary because 1 is finite. Now that we have reduced the polynomials that we are considering, can we hope for something like this? A finite set is entirely characterized by its cardinality. And so instead of having span between all sets and 1, maybe if we replace all sets by just natural numbers, we might get what we want. And here we need to take a step back and remember that the polynomials and the spans form bicategories. So here, this is actually a groupoid, and this is also a groupoid. So this equivalent sign here, we want it to be an equivalence of groupoids. And even though those two groupoids have isomorphic isomorphism classes, they are not equivalent as groupoids. For instance, if you take the polynomial x times x, it has a non-trivial automorphism, which just swaps the two variables. And if you see the corresponding span between one and between the natural numbers and one, it's the span with just the singleton here, and that selects the exponent of this x squared here, so just selects 2. And this span here doesn't have any automorphism, because an automorphism of spans would be a map from one to itself, such that some equalities hold. And there is only one map from one to itself. So in some sense, if we want to actually have an equivalence of groupoids, what we really need here is not the natural numbers, but the groupoid of finite sets. If here we have the groupoid of finite sets, then even though there is only one map between one and itself, asking for commutativity will actually be a data. And this data will be encoded by the fact that in finite sets, the set with two elements has two automorphisms. And this non-trivial automorphism will exactly represent the swapping of the polynomial x squared. So what we observed is that in order to hope for this model of linear logic, we're going to need to only consider finite real polynomials and to also enlarge the objects to consider groupoids as possible objects. Because here, the groupoid of finite sets is not a set because of all the automorphisms that we need. And this is exactly the same requirements that were used like 3 years ago by my advisors and his collaborators to get a Cartesian closed bicategory of polynomial functors. And there will be a reason for that I'm going to talk about later when I get to all our results. And the thing is, when we work with groupoids, there are a lot of issues coming from the fact that groupoids do not form a category, or at least they do in some sense, but as a category, it's not a locally Cartesian closed category. So you can consider groupoids and functors, but the thing is that the right notion of equivalence between groupoids is not isomorphism, it's something weaker. And so actually we need to work up to homotopy. So I'm using the word homotopy here. Some people like to use words like pseudo stuff or weak stuff, and homotopy here is really in this sense. So if we consider the bicategory of groupoids, we see that it is a locally Cartesian closed bicategory. So groupoids from a locally Cartesian closed thing up to homotopy. And this is really essential because when we take the pullbacks constructions, for instance, to compose spans in groupoids, or the more complicated stuff we do when we compose polynomial diagrams, we really need to do the pullbacks as homotopy pullbacks or weak pullbacks, pseudo pullbacks for those who like different terminology. So this is not just fancy for nothing. And now something that might be more fancy for nothing is working in homotopy type theory. So actually working in a bicategory of groupoids is harder than working with sets because bicategories are more complicated than categories. And if we want to consider spans and polynomials in groupoids, we're going to have not bicategories, but tri-categories. And this really starts to be very complicated to work with. And so we work in a setting, which is the setting of homotopy type theory, in which everything is automatically right from the point of view of homotopy. So what is homotopy type theory? It's an extension of Martinov type theory, in which we have types as ordinary type theory, but they are thought of as spaces, not as sets. And in particular, sets will still be types because sets are just discrete spaces, but we also get groupoids as types, two groupoids, higher groupoids, and all of this just lives nicely in the same world. And all the maps between types are automatically functorial with respect to this groupoid structure. And all the constructions are homotopy invariant. So just a few examples of what this means. When you do quotients in homotopy type theory, instead of equating elements, you add identifications, you add paths between them. And so, for instance, if you start from 2 points and quotient them, you get just 1 point. But if you quotient it even further, you get a circle or something that has more paths. Similarly, when you do a sigma type, it's not just a disjoint union, because if the sigma type is taken indexed over a groupoid, then the structure of the groupoids appears in the global union. And so it's actually more like a Grothendieck construction for groupoids. And all the fibers and pullbacks and all limits and limits are taken in the homotopical sense, because that's how things work natively in homotopy type theory. So in homotopy, in this type theory, we can do the same as before and define polynomials and spans, but replace everywhere sets by types in the definitions. Just for the notion of finiteness, we still require the exponents to be finite sets, seen as discrete types. There are other notions of finite types, but I'm not going to talk about that because here we're still interested in those finite sets. Because the type of finite sets and bijections is now a type, and it's just a groupoid. And here we can actually prove this equivalence of types in hot. So we can define bang of 1 to be the type of finite sets and bijections. And more generally, if we define bang of some type I to be the type of finite sets together with a coloring by I, so pairs of a finite set and a map to I, we can show this equivalence of types in full generality for all types I and J. So this is even stronger than just sets I and J, it's all types I and J. And the way the proof works in hot, so this is maybe the most technical slide of the talk, is just by basically reasoning with the chain of equivalencies using a lot of very standard lemmas of homotopy type theory. So first, a polynomial, finite ray polynomial between I and J is by definition the data of 2 types E and B. So this is here, a map from E to I, a map from B to J, and a map from E to B with finite fibers, which is what this notation here means. We can just reorder these things. I'm just putting this here and this here, and the E comes here, and the B comes here. This is just reordering a tuple. And now here, the data of a finite type together with, sorry, not a finite type, but a type together with a finite fibers map to B is the same thing as a family of finite types indexed over B. And the coloring of the total family is the coloring of the total family on the other side of this equivalence. And here, this pair of things can also be rewritten by refactoring as a family of finite types together with colorings of all these elements of those families. And this here is exactly what I wrote before as bang I. And the data of a type B together with a map to bang I and a map to J is exactly the same thing as a span from bang I to J. So in homotopy type theory, the proof is almost elementary. Whereas if we wanted to work in the bar category of groupoids, we would have to, all the sigma would be like Grothendieck constructions. And this equivalence would be a weak equivalence of bicategories, and we would have a lot of mess. And here we just get everything very naturally, and we don't even, and we got it for all types. So even higher groupoids and this kind of stuff, we get for free. Now, a slight parenthesis, because I'm working in homotopy type theory, and I'm saying we have like those kinds of higher categories. But what does it actually mean? So, as I said before, if we consider polynomials and spans in groupoids, we get tri-categories. And if we generalize from groupoids to types, arbitrary types, we should get something that's like an infinity category. So all the associativity laws and the would hold only up to isomorphism, and all those isomorphisms would only hold up to covariance laws, and we would get into covariance hell. And it's known that in homotopy type theory, it's not known how to do all this stuff all the way up to infinity. And so what we actually do is that we just discount all the higher covariances and just prove the base ones, which seems like we are actually not proving that many things. So the notion is the notion of wide categories. Basically, you take the definition of categories, but you replace sets with types, and you don't ask any coherences beyond associativity. You ask associativity and unitality, but no triangle or pentagon axioms, nothing of the sort. And even though this seems like a way less strong notion, actually everything that can be proven in homotopy type theory using universal properties can actually be shown meta-theoretically to be homotopy coherent all the way up to infinity. So if we show that we have a Cartesian closed wide category, even though wide categories are not that much structure, if we know from outside the theory that this is actually an infinity category, we know that it is Cartesian closed in the infinity categorical sense. So I can tell more about this later if people ask me questions about it. But now let's talk about our actual results. So I talked about the fact that we can define this bang, and this bang is an underfunctor on the category of spans, and actually it has a commonad structure. And with respect to this commonad structure, with respect to this commonad structure, the Kleistli category for this commonad is equivalent to the category of finitely polynomial functors. This is basically the equivalence that I wrote before. Polynomials from I to j are equivalent to spans between bang I and j. And what I'm saying here is that this equivalence also respects composition of polynomials on one side and composition of spans between bang I and j on the other side with respect to the laws given by this commonad. And moreover, the category of spans, the wide category of spans, together with this modality, has a compatible symmetric modular structure, making it a silly category, which is one possible definition of a model of intuitionistic linear logic. And the category of spans is also compact closed, which implies it is autonomous. And so we get a full model of classical linear logic. And there's a very abstract result that tells you that if you have a silly category, its Kleistli category is Cartesian closed. And so we get as a direct corollary this result from 3 years ago that the category of finitary polynomial functors in types is a Cartesian closed category. And so if you know it's an infinity category, you know that it's actually a Cartesian closed infinity category. Now, I've talked a lot about finiteness, but actually we don't need finiteness. We just need any notion of smallness. So if you remember before, the issue was that we cannot take the set of all sets. So we had to restrict to something smaller, and any right notion of smallness will work. So in type theory, we have notion of smallness given by universes. So if you have a universe U of big types and a universe V of small types living inside you, closed under suitable constructions, you can define polynomials to be V array if all the exponents are types in V, and you can define bang with respect to V to be the pairs of a V small type E together with a coloring by I. And then you will get exactly the same result as before, that V array polynomials between I and J correspond to spans between bang Vi and J. And you also get all the silly category and the model of classical linear logic, the compact closeness, and all of this. And so I've written just a few examples below. If you take V to be finite sets and U to be groupoids, you get the original model we had in mind, but you could take in type theory V to be all sets and all small sets and U to be large groupoids, or you could even take V to be groupoids and U to be all types. And what this would mean is that you allow polynomials with exponents which are themselves non-sets, so something like x to the power of the circle. So a few examples of polynomials that you get in this way. So if you take the map from finite pointed sets to finite sets, the fiber over a finite set E will itself be a set of size E, will itself be E. And so the polynomial associated to this map is a polynomial from time to type that sends a type X to the type of finite sets colored by X. So this is actually our bank commonad. It itself is a polynomial in groupoids. And now for another example, if you take a map that sends a natural number to this monstrosity here, So this is actually just a group weight whose objects are natural numbers, and where the automorphisms of the natural number n are given by the group of z over z, so the secret group on n elements. And the fiber over n will itself be this set with n elements. But the sum is taken in a weird way because it's a sum over a group weight. And so the actual function that you get is a function that maps x to the sum of x to the n quotiented by the action of z over z. So this is the type of cyclic lists. And generally, there's a thing in the higher category theory that if you sum over a group weight, if you take a Grothendieck construction over a group weight, it amounts to quotienting the summand by the action of this group weight. So if you like to think of polynomials as data structures, considering polynomials in group weights allows you to consider data structures with quotients. So if you take just the sum of the xn, you get lists, which is an ordinary data structures. And if you consider the quotients by the symmetric groups, you would get multisets, which is basically our commandant here, which we've shown is polynomial. And now for a final, very weird example. So I said that you could consider polynomials in arbitrary types, and it still makes sense. And so we can leverage homotopy theory to get very weird examples. So there's this thing in homotopy theory called the Hopf migration. That's a map from the 3-sphere to the 2-sphere, whose fibers are 1-spheres, so circles. So I've written this equivalence here that the fiber over x is a circle. Between those weird symbols here, if you don't know what this means in homotopy type theory, just think of it as big quotation marks. Because even though this is an equivalence, we don't have that the total type is the product of S2 over S1, rather that it is S3. So this is a non-trivial family of circles indexed over the sphere, such that the union is the 3-sphere. And if we consider the corresponding polynomial, well, formally we get this expression. And so this expression looks like something like S2 times x to the S1, but in the globally twisted way. And x to the S1 is the type of maps from the circle to x. So it will be like the loops in x in some way. And we're considering all loops in x, but in a way that's globally twisted above the sphere. And basically, I have no idea what this is, and neither does Samuel. So if you have any idea of what those kind of things can represent, and if it can be useful for anything, please reach out and tell us. So now, as a summary of what we did, we arranged the usual notions of spans and polynomials into a model of linear logic using ideas from homotopy type theory. And what might come next is investigating a differential structure, because there's this notion of differential linear logic, where instead of just having this one adjunction between linear maps and nonlinear maps, you can also differentiate nonlinear maps to get back linear ones. And also, we could compare this model to other homotopically flavored models of linear logic. So we could investigate potential models of linear logic inspired by other infinity categorical phenomena. So there are those notions of from homotopy theory, which represent kind of linear notions in the infinity categorical setting. And finally, we could compare with some other stuff in the literature. So there are other models of linear logic based on spans, and also models based on general species of structure, which basically have the same story as spans and polynomials, but with profunctors replacing spans. So that's all for me. Thank you very much. Okay, so yeah, we did a lot of formalization in Agda, but it's not like open or public yet because it's basically a mess. The thing is, when you actually want to formalize all of those things, I talked about like the definition, fiber definition of polynomials, but in type theory, it's easier to work with an index version. And so we had a lot of different attempts by checking what we should take as fibered and what we should take as indexed. And so there's a lot of things we need to sort out to have the most beautiful presentation possible, but we might actually make it public at some point. So yeah, we have some kind of In cubical like that, actually.
I also have a quick question for you before we move on, but you know, this model of linear logic is a very bad model of linear logic because it's a compact closed category. So conjunctions and disjunctions and implications are always the same. So if you're thinking more logically, can you use your homotopy type theory to make it a less logically problematic model?
That's a good question. So I don't really know the answer to that. I'm not sure if we can tweak this model we're using ideas from homotopy to make it more logically interesting. There are ways in general to make like those kind of degenerate models of linear logic into non-degenerate ones, but since it's a kind of free way, it's not necessarily that interesting either. But some of the other potential models that I hinted at here might have some more interesting logical factors.
Okay, we kind of have to go. We sort of said to start setting out, but thank you very much.